So here's our first question. Light that's moving through a vacuum has a frequency of 560 terahertz. And so remember, capital T is that tera root prefix. And so the question is, what is the color of the light? So to figure this out, we look at over our table, or sort of our picture, our illustration that we have over on the right side. And so this shows us the different colors of visible light going from red all the way up through violet. So we have the whole Roy G. Biv, the rainbow over here. And it gives us the wavelength of each one of those nanometers. And so violet light's between 380 nanometers and 435 nanometers. And so blue light has a wavelength between 435 and 500 nanometers. And so in order to figure out the color, we're going to need to know the wavelength. And so remember, wavelength is lambda, is the unit that we have here, and that our equation for figuring this out is that speed, v, equals frequency times wavelength. So v equals f lambda. I just flipped them around here, but they mean the same thing. Remember, multiplication, the order doesn't matter in a case like this. So frequency, the speed is equal to frequency times wavelength. So let's see what we know here. So let's look at speed first. Speed of the wave, this is light. Light's electromagnetic wave. And so remember that the speed of the light depends on what substance it's going through. In this case, it says it's in a vacuum. Vacuum is just another word for empty space. And we said that the speed of light in a vacuum, just FYI, that is actually got its own little letter for it. It's lowercase c. Is this used for the speed of light in a vacuum, is 3.0 times 10 to the 8th meters per second. And that's in the right units, the one we want. So we'll say, to start this off, 3.0 times 10 to the 8th meters per second is going to be equal to the frequency, and it tells us the frequency, 560 terahertz. Problem is, that's really not in the unit that we want it to be in. So we're going to have to do a little bit of a unit conversion here. So to figure this out, we'll say, okay, 560 terahertz. We'll see if we can fit it in here. We want to cancel out terahertz, and we want to go to hertz because that's the unit that we want here. So this is just straight up metric conversion in this case. So we know the terahertz is going to get a 1 because it has the prefix on here. Hertz would be whatever tera is. And so tera should be 10 to the 12th power if you look at your metric prefixes. So for this, we do 560 times 10 to the 12th power divided by 1. And so that ends up being 5.6 times 10 to the 14th. And so if we put in the frequency, we get 5.6 times 10 to the 14th hertz would be our frequency, extremely high frequency. And so we've got that. Then times the wavelength, which we don't know. That's our lambda. So we've got that set up. So 3 times 10 to the 8th meters per second, the right unit here, equals 5.6 times 10 to the 14th hertz times lambda. Now at this point, it's just a matter of solving this out. We want to get lambda by itself, so we'll divide both sides by 5.6 times 10 to the 14th. So divided both sides by 5.6 times 10 to the 14th, like that. And so grabbing our calculators on there, we get 3 times 10 to the 8th divided by 5.6 times 10 to the 14th. And so I get 5.35714 times 10 to the negative 7th. So we'll write that out. So I get, we said 5.357, 143, I'll round it right there, times 10 to the negative 7th. And then the unit of lambda is the unit of our wavelength, we said, is going to be meters. All right, so 5.357143 times 10 to the negative 7th meters. Well, let's look at our table over here, our illustration. Well, it has the wavelength, but it's in nanometers. So we're going to have to do another unit conversion. So we're going to take this guy right here, set him up. We want to get rid of meters. We want to go to nanometers. And so same as we did before is that nano is 10 to the negative 9th. And so we say 10 to the negative 9th meters over there. So that should cancel out meters and get us to nanometers. And so now it's just a matter of doing the math here. So 5.35714 times 10 to the negative 7th divided by 10 to the negative 9th right there. And so I get 535.7. So 535.7143. And that's going to be in nanometers. Okay. Significant figure-wise is that 560 has 2 sig figs right here. The speed of light, 3.0 times 10 to the 8th, that's considered, we're going to consider that to be exact for purposes here. That's a conversion factor. It's a constant, I mean. So we'll leave that, will not affect it. So our final answer should have 2 sig figs. So this should be 540 nanometers would be our wavelength. And now we can look over here and see where is 540. Well, 520 is right here. 500's up there, 565's here, so 540 would be somewhere in the middle of this section here, so it would be green light. And so if I had a light with a frequency of 560 terahertz, it must be green light. All right, now let's try another one here. What's a possible frequency for an X-ray in empty space? Now we have another illustration here. This one telling us wavelength for different types of electromagnetic radiation. But in this case, the question is about X-rays. So we look on X-rays in this range right here. X-rays look to be somewhere between 10 to the negative 11th meters and somewhere between a nanometer and a tenth of a micrometer. So it just says what's a possible frequency. So really all we have to do is pick some wavelength that we know is in the X-ray, and I'm just going to go ahead and pick 1 nanometer. It's right in the middle of that X-ray range. So we'll say that. So we're going to say that our wavelength is going to be 1 nanometer. We know we're going to need to put it into our V equals F lambda to figure this out, but we don't have the right units. So we're going to go ahead and say, all right, let's put it in 1 nanometer. And so we want to get rid of nanometers. We want to go to meters. 1 nanometer is 10 to the negative 9th meters right over there. And so we should just be able to do our math on this. So really just 1 times 10 to the negative 9th is just 10 to the negative 9th. Very easy math. And so that should be meters right there because we've canceled out nanometers. So 10 to the negative 9th meters is what our wavelength is. So now we can set up our equation. V equals F lambda. So V is the speed, depends on what substance is traveling through, but it says here we're traveling through empty space. Well, in empty space, the speed of light is just our normal value of 3 times 10 to the 8th meters per second, and meters per second is the unit we want there, so that's good. Equals frequency, we don't know the frequency, times the wavelength. We already figured out the wavelength is 10 to the negative 9th is in meters because that's the unit that we want. Now at this point, it's just once again a matter of solving for the frequency. So we'll divide both sides by 10 to the negative 9th. 10 to the negative 9th, and so frequency should be just 3 times 10 to the 8th, which our speed of light, divided by 10 to the negative 9th. And so 10 to the negative 9th, and so I get 3 times 10 to the 17th is what I get for this right here. And so 3 times 10 to the 17th power, the units are going to be hertz. Significant figure-wise, we'll have to go back to what our original measurement was here. So this 1 nanometer has 1 sig fig, so our final answer should have 1 sig fig, and it already does, so that's pretty good. So 3 times 10 to the 17th hertz would be a possible frequency for an X-ray in empty space. Looking at energy. So here's our next question. What's the energy of a single photon with a frequency of 3.22 gigahertz? So we're looking for energy in this case. And so energy, we're going to use Planck's equation that said that energy is equal to H times F. Okay? And so we want to find energy. It's 2 things we need to know. We need to know H and we need to know F. So to find our energy here, we say energy is equal to H. H is Planck's constant. Well, what's Planck's constant? We'll have to look back. So for Planck's constant, does it tell us what it is? Back here, there it is, 6.626 times 10 to the negative 34th, way down here, right? So 6.626 times 10 to the negative 34th is Planck's constant. So 6.6266 times 10 to the negative 34th. All right, so we got Planck's constant. Next one we want here is the frequency. So the frequency is 3.22 gigahertz, but we need it to be in hertz for this to work out right because we want our energy to come out in joules. So we're going to have to convert. So we say 3.22 gigahertz. Set this up, cancel out gigahertz. Go to hertz, which is what we want. And so 1 gigahertz is 10 to the 9th power. So we have 10 to the 9th, so it cancels out gigahertz. 3.22 times 10 to the 9th divided by 1 is, well, just 3.22 times 10 to the 9th. So 3.22 times 10 to the 9th power hertz, which is our right unit here. All right, at this point, we should be able to go ahead and do the math on this. So the energy is going to be equal to 6.626 times 10 to the negative 34th, and then times 3.22 times 10 to the 9th. And so I get 2.1335 times 10 to the negative 24th. So so we said 2.1333572 times 10 to the negative 24th. And the units there is energy, since we used our right units we used the Planck's constant, which has the units in the right thing here. We use frequency in hertz, so this should be in joules for our energy here. Now, that's an awfully small energy. Well, the reason why is because this was only one photon, right? Just one single photon. So the very smallest particle of light that you could have isn't going to give you much energy. So we don't know much about this frequency, about whether that's considered to be a high frequency or a low frequency anyway. But last step here, we do have to round this to the right number of sig figs. The value we have here is the Planck's constant is a constant, so it's infinite sig figs. The 3.22 times 10 to the 9th would be 3 sig figs because it came from this number right here. So we'll round our final answer to 3 sig figs. So 2.13 times 10 to the negative 24th joules right there. That must be the energy of this one photon. All right. So our next question here. An electron is emitted from an atom with an energy of 1.99 electron volts, eV. What type of electromagnetic radiation is emitted? All right, so we've got our whole list over here of the different types of electromagnetic radiation: gamma, X-rays, UV, visible light, infrared, microwave, radio waves, and we'll have to figure out what type it is. And so fortunately here we have both the wavelength and the frequency, so we can get either one to tell off of this particular table. So we'll just need to figure out either one. But we know it has an energy of 1.99 EV. Now, EV is not a unit of energy we've seen before, which means we're going to have to convert it. Now, we know to get this to work, we'll have to use our energy is equal to H times F. So we know the energy is 1.99 EV, but the energy here needs to be in joules. So we're going to set this up and say 1.99 electron volts, and we're going to want to cancel electron volts. We want to go to joules. So do we have a conversion factor? Well, it tells us the conversion factor right here. 1 electron volt is equal to 1.602 times 10 to the negative 19th joules. So I can go ahead and say that 1 electron volt is 1.602 times 10 to the negative 19th joules. It's a 9 right there. That cancels out electron volts, and we should just get joules this way. So I should be able to go ahead and do this calculation. So we say 1.99 times 1.602 times 10 to the negative 19th. So I get 3.18798 times 10 to the negative 19th. All right. So this would be in joules. So we can go ahead and write this in for our energy. So 3.18798 times 10 to the negative 19th joules. Once again, it's a very, very small number because this electron is just a single electron. Now, hey, wait a minute. This E right here is the energy of the light, but it says this energy right here is the energy of the electron. So what do we do in that case? Well, remember our photoelectric effect? Photoelectric effect said that the energy of the electron depended on the energy of the light that's coming in. And so due to conservation of energy is that the energy of this electron that comes off came from the energy of the light. And so that means that, and actually I miswrote this here. That means that the energy of electromagnetic radiation should be the same as the energy of the ejected electron. Now I said what type of electromagnetic radiation is emitted. That should be absorbed right there. That was a mistake in writing out that question, because what happens is the electromagnetic radiation comes in, hits the plate, the piece of metal, it's absorbed, and then the electron gets kicked off because the electron takes the electromagnetic radiation's energy here. And so really we're trying to figure out what type of EM radiation is absorbed here. But either way, it doesn't change on how we set this up. So we have an energy we've already figured out, 3.18798 times 10 to the negative 19th joules equals H times F. So H, remember, is Planck's constant. So if you don't remember what it is, we look back again and we say, okay, 6.626 times 10 to the negative 34th. So 6.62626 times 10 to the negative 34th right there. And then times our frequency, which we don't know. So sort of written off to the side here, but we'll see what we can do. We want to divide both sides by our Planck's constant. So 6.626 times 10 to the negative 34th. That's a 10 to the negative 34th right here. Same thing here, 6.626 times 10 to the negative 34th. And so that should cancel our Planck's constants over here, and we should be able to find our frequency. So 3.18798 times 10 to the negative 19th divided by 6.626 times 10 to the negative 34th. And that gives us 4.811 times 10 to the 14th. All right, so let's see what we can do with this one. So we get a frequency of 4.81, that's an 8, 1, 319 times 10 to the positive 14th. Significant figure-wise, really the number we started with was this 1.99 electron volts, so it'll be 3 sig figs. So this will end up being 4.81. Can't draw my 8s very well today. 81 times 10 to the 14th, and the unit here is going to be hertz, because that's the unit we get out of our equation here. So that's going to be our answer here. Now the question was, what type of electromagnetic radiation? So 4.81 times 10 to the 14th. And so that's a frequency. So we're going to look over on the frequency side. So looking down, 10 to the 14th is right here. We're bigger than 10 to the 14th because it's 4 times 10, almost 5 times 10 to the 14th. So that's going to be about halfway up to 10 to the 15th. So we're really talking about somewhere right in here. But that's sort of borderline, isn't it? Because we got some UV could be here. We've got some visible light that could be here. We've got some infrared that could be here. It looks like we need to zoom in a little bit. So if you remember, we did have a diagram earlier about visible light. Where was it hiding? Here it was. And so we could look at that one to see. So let's go back and take a look at what we had. We got 4.81 times 10 to the 14th hertz. Well, if we were to go and unit convert that, we could go from hertz. Actually, we can't do that. That's going to be in wavelength. We have to convert to wavelength first to do that. We could do that if we needed to, right? Because we could always just go and use our V equals F lambda, that our speed equals frequency times wavelength, to figure that out. But in this case right here is that it looks like it's going to either be visible light, ultraviolet, or infrared.